Hello everybody. Today we are going to compare the various models of the atom using a simulation. As you can see, we've got a light gun to fire at a box of hydrogen atoms. We can select either white light containing photons of all wavelengths or monochromatic light containing photons of a single wavelength. We can even select the wavelength using this slider. We can select the atomic model of interest here and view what happens during our experiment here. We can also keep track of hydrogen's emission spectrum here. Let's start with Dalton's model. Note the absence of subatomic particles. When we turn on the light gun and use white light, photons of any color are reflected. Switching to monochromatic light confirms this. Let's speed up the action to see what, if any, spectrum develops. Thomson's plum pudding model is next. We now have a particle-like electron contained within the atom's positive charge. Thomson didn't think that the atom's positive charge was contained in a particle since protons had not yet been discovered. Let's turn on the gun. Note that most photons proceed straight through the atom. Those that are absorbed knock the electron around. Remember, it's a particle. In response, the electron emits light, but only one wavelength. The electron is not quantized in this model. Rutherford's model is next. Note that we have a proton in the nucleus with an electron orbiting like a planet around the sun, hence the term solar system model. Let's turn on the gun and I believe the result speaks for itself. Let's turn our attention to Bohr's model. We still have Rutherford's nucleus, but now the electron has been quantized. It can occupy only certain energy levels. As we turn on the gun, we can see that electrons absorb only certain photons to become excited, and then release the same photons when returning to ground state. Speeding up the action allows us to see all four lines in hydrogen's visible spectrum developing, plus a few lines in both its IR and UV spectra. Let's have a look at de Broglie's model. Recall that de Broglie showed that the electron's mass is so small it has a measurable wavelength and therefore is more like a wave than a particle. So we still see that the electron is absorbing and emitting only certain photons, but that changes the electron's wavelength. It is no longer a particle. Changing its wavelength changes its frequency and energy, just like any other electromagnetic radiation. Let's observe these events in 3D. We can more clearly see the changes in wavelength from this angle. Let's not forget to check our spectrum. We can see the same lines in the emission spectrum that are characteristic of hydrogen. They are being produced, however, by a wave absorbing and emitting photons, not a particle. Last but not least, we have Schrödinger's model. Hydrogen's electron is no longer a wave with a measurable wavelength, but a cloud of negative charge. Let's turn on the light gun. When an electron is excited according to this model, its cloud not only enlarges but can also change shape if it moves to a different sublevel, from an S to a P sublevel, for example. By definition, an excited electron is violating the Aufbau principle. Note the changes in the quantum numbers here, energy level N, sublevel L, and orbital M, respectively. Again, speeding up the action shows that the electron clouds are still absorbing and emitting the photons characteristic of hydrogen's spectrum. So there we have it. No electrons, to bouncing particles, to orbiting particles, to quantized orbiting particles, to quantized waves, to quantized electron clouds. If you'd like the opportunity to explore with this simulation on your own, you can find it in Schoology in the Electrons folder under Models of the Atom. Just click on the link. And then click here to run, and your computer will download the app. That's all for now. Thanks for watching.